Hello everyone, and welcome back to a new episode of Advent of Code. We are going through the backlog of a few problems that I solved off camera, and we are now up to episode 16. Day 16, I suppose. Not episode 16, because I did a couple of days in a single episode. Anyway, Day 16, Permutation Promenade. You come upon a very unusual sight. A group of programs here appear to be dancing. There are 16 programs in total, named A through P. They start by standing in a line. A stands in position 0, B stands in position 1, and so on until P, which stands in position 15. The program's dance consists of a sequence of dance moves. Spin, written SX, makes X programs move from the end to the front but maintain their orders otherwise. So they stay, whoever was in front, in the very front of the line, becomes the furthest forward of the programs who are moving. But they all, as a group, move to the back. Exchange, written XA/B, makes the programs at A and B swap places. Partner, written PA/B, makes the programs named A and B swap places. So we take, they give a couple examples here. S1 moves A to the back of the line. No. From the end to the front, not the front to the end. Okay. Makes E move to the front then. Fine. X3/4 swaps the programs in the third and fourth, i.e. second last and last positions. And PE/B swaps the programs named E and B. And they say, okay, you watch them dance, and then say in what order are they standing after the dance is over. Fine. So, okay, let's write a program, I guess, right? The first thing to do is to build a model of the domain, right? We're not going to get anywhere without a good model. And the only really interesting thing, I think, here is a dance operation. And there are three kinds of dance operations. There is a spin, modified by an integer. There is an exchange, modified by two integers. And there's a partner swapping operation, modified by two dancers. And so we could, of course, have written a type alias for dancer, dancer called char or whatever, but I don't think that is that useful. So, okay, a simple thing to do first is to parse a string. Let's actually go look at our input real quick. It looks like this. A bunch of values separated by, bunch of operations separated by commas. I would have expected them to be separated by new lines. Sadly, they were not. Anyway, so supposing that we had the string for a single dance operation, how would we parse it into an op? Well, look at the first character. If it's an S followed by some stuff, then we just call read on the stuff, which is a list of characters representing an integer amount to spin by, and we wrap that up in a spin. Otherwise, it must be something else followed by more, i.e. not an S. I feel like this whole program would have been simpler if I had just not had this extra case here. Yeah, I don't know. So, I could have, of course, removed that initial clause and put an S here, right? Spin, read more, right? And that feels cleaner to me, but also there's this quote problem, which is that this where clause applies to the entirety of this body of parse. And in the case that there is an S and we're spinning, we don't really want to call break and split it up on a slash and look at the before and the after and so on. Right? And I think it would actually, it seems wasteful to do that. It actually doesn't matter because of laziness, right? This body never refers to before or after, and therefore this pattern match never occurs, I think. And therefore this function body never gets called either. But I don't know. I think it's clearer to put it up here, outside the scope of that where clause, to make it very explicit that this where clause only applies to the x and p cases. Anyway, so we call break on =/. We've looked at break before. It splits up a list according to a predicate, giving you the values before the predicate and starting with the predicate. And so we just say, okay, well, the values before, that's a list of characters, i.e. a string. The stuff coming after, well, strip out that leading slash, but then it's a list of characters. And we'll just read them both. Sorry, we won't necessarily read them both. If we're calling an exchange of two numbers, then we should read them and get two ints. If we're swapping two partners, then before and after should both be a single character long, and therefore we should just call head to convert the list of a single character into the character itself. This is unsafe. There are input formats where this would well, this is not the only unsafe thing about this parser. This parser depends on being passed a correct input. There are a lot of ways it'll break if the input is incorrect. But okay, you know, head is the least of our problems, sort of. Like read has the same problem. Anytime you call read, it could break if the input value is broken, is not correct. And there are other functions you can use if you want to be more careful about such a thing. But here we're guaranteed that Eric always gives us valid inputs, and we just want to read them. So okay. And how we split on the commas the input is like really easy. We've done this before. I probably just copied this from some previous puzzle. So having defined our operation type, the obvious thing to do next is to write a function which applies a single operation to a string of dancers. And it's pretty simple. To spin, i.e. move some stuff from the back, we figure out the size of the segment that we're moving and the size of the segment that's standing still. We drop the segment that's standing still. Or is this technically the segment that's moving? No, it's the segment that's standing still. We're moving programs from the back to the front. Ah, yes. We drop all the things that are standing still, giving us only the things that are moving, and we put them in front of, i.e. concatenate them with, taking all the programs that are standing still. And the number of things to drop is just the length minus the number that are moving. It seems like we maybe didn't need this at all. Yeah, we did, because we're looking at the string backward. Okay. To apply an exchange, we need to know the indices that these programs are at. So we zip a 2-argument function over a list of indices and the values themselves. So rather than just... So of course, if we had fast random access array type things, we would just look up those 2 indices, swap them, and return the value. And as I've said in many, many previous episodes, such data structures do exist for Haskell, but like, I don't really know how to use them properly, and they seem kind of hard. And modeling most things in terms of lazy operations on linked lists is relatively simple and usually not too expensive compared to doing it right, but, you know, sometimes it could be expensive enough that you would want to actually do it right instead. So anyway, to exchange, we zip a function over the indices and the values, where basically the exchange function just says, well, if the index that you're at was the old value, then please go look up what's at the new value. And again, this is a slow lookup operation, but that's life. And if you were the new value, then go look up the old value, and otherwise stay the same. And we do something similar for partners. We map, only this time we don't need indices, thank goodness. we just map a swapping operation where we say if you were the old thing, be the new thing. If you were the new thing, be the old thing. Otherwise, stay the same. And that's sort of like all there is to this whole problem. We call lines, we get the first line, we split it up by commas, we map parse to get a list of operations to perform, and we call states, where states is a function from list of op to list of string that produces all of the states that the programs ever enter. And states is a... So again, I could just produce the final value, but when possible, I find it useful to produce a list of all states because you never know when we'll be asked questions like, maybe part 2 is going to say, how many times during the dance did the string begin with BM? And you're like, oh, well, wish I had the list of states. And it's sort of free to produce that list because we're being lazy about things. So anyway, so we do a scanl, which remember is like a fold L, except that it produces a list of the values it ever saw. With our apply function and the starting string, which is the letters A through P. And that works fine. So let us go look at part 2. Here was the answer, by the way. Now that you're starting to get a feel for the dance moves, you turn your attention to the dance as a whole. Keeping the positions they ended up in from their previous dance, the programs perform it again and again, including the first dance, a total of 1 billion times. In what order are they standing after their billion dances? So the first thought, of course, might be, well, let's run the program a billion times, right? So something I wanted to try was, let's time it. How long does it take? We ran with compile optimizations on. It takes, well, 1/5 of a second to compute the answer. Okay. How much is 1/5 of a second? Could we afford to run this a billion times? It seems like it would take a while, but maybe seconds are shorter than I thought, right? So let's fire it up. Well, first of all, to multiply 1/5 of a billion by 1 billion, we get 200 million, right? So I didn't actually do this operation. I could... Really? You can tell I didn't do this operation. Because Units isn't installed. But something that... Units is a great program. I love Units. It'll do unit conversions for you, so you don't have to look them up. Of course, these days you can just type it into Google, but it's kind of nice to have this prompt up. So how long do I have? I have 200 million seconds. Could I get that in months? Is months a unit? Probably not, actually. Let's just get it in years. 6 years. So we'll be here a while if we try to do it that way. Even if we can speed the program up by a factor of 100, it would still take over a month. So, well, 6, about a month. So we're probably not going to speed the program up by that much. So that's clearly the wrong approach to take. So what to do instead? Basically, the only reasonable thing I could think of was to, at some point, this dance must loop. I don't know about must, but actually, let's find out. Must it loop? Here I have a REPL, and we know that there are 16 programs, right? What is the product of 1 to 16 as an integer, if you would be so kind? I see. Well, it is not the case that it must repeat within a billion tries. Right, there's million. There's 20 trillion different ways these programs could line up. And so if their dance operation certainly could go on a billion times without ever repeating anything, if it were a very good hashing function. But the thing is, if it does that, I really could not figure out any way to figure out an answer. How else could you shortcut this? If it never repeats, you would have to do some very careful analysis of the dance and maybe figure out some common properties that you could extract along. I don't know. It seems very hard to me. And so I thought, look, let's just find out if they repeat. Hello, do I have... I should have day... Oh! Oh, was there a change to day 15 that we didn't check in? Yes, the new type wrapping. Let's commit that. Add a new type wrapper to prevent programmer errors. Okay. So what I meant to do was check out this and get to part 2. And so basically my idea was, let's write a function that a generic function for any instead of applying just to dancers, applies to anything you can put into a map. And it says, tell me, you want to iterate this function n times. Tell me what the function is, how many times to iterate it, and where to start, and I'll get you an answer as fast as possible. And basically what it does is it just iterates, and every time it does, it puts the value in the map until it sees a value that it's seen before. And then it says, okay, well, what's my current iteration? What iteration did I last see that at? That's how long the loop is. I can skip in chunks of that length, which sounds like modular arithmetic to me. Right? We sort of found out we're in a loop of size m, and therefore we can work modulo m, and we reduce the remaining number of iterations to apply modulo m, and get our answer. So the idea is, shortcut of f is go, our auxiliary function, starting with an empty map. And so of course go takes 3 arguments. We pulled one of them off as f to keep in scope. The other 2 we allowed to be passed on to go, and it also takes a map. So go takes a map, the int from the original function, and the initial value. And if we need to go 0 times, just return the value. We're done. Don't iterate at all. Otherwise, look up the value x, what we're currently iterating on, in M. If there's nothing there, then add it to the map labeled with n, and call yourself recursively, that is go, asking for iteration n minus 1 of not x, but f of x. Iterate it once, right? Iterate fx once and say, compute it n minus 1 times. And we're sort of maintaining the invariant there. Okay, I'm back. I've told you guys before that I need to get... What have I done? That I need to get a new mic stand, and because I keep bumping the mic on this very short cable, perched precariously where it is, and it falls, and I have to like edit things. It's a pain. Anyway, so we maintain the invariant that we want to iterate x n times by iterating it once and then reducing by 1 the number of times we want to iterate it. Sort of simple recursive stuff. And if we did find it in the map, then we know what iteration we saw it at previously, or previously how many iterations were there to go, and we can subtract how many iterations there still are to go and find out how long the loop is and work modulo that. So we just take our n, modulo the size of the loop, and then we just call shortcut again. This is like kind of a silly little hack, I think. In principle, at this point, we would just call the ordinary iterate and say, hey, iterate, take n, the nth value of iterating this many times, whatever. But I didn't want to have to write iterate and this bang operator, and I already have a function that does that for me, right? It's shortcut. It does some needless extra work of building the lookup map again for no real reason. But that's life. So that's all done. And now that we have that function, implementing part 2 is very simple. First of all, I gave up on the scanl thing because I now know we don't need it. And dance is just a function taking a list of operations and returning a function from string to string. Now, we could have said taking a list of operations in a string and producing a string. But remember, that's the same as this, taking a list of operations and producing a function from string to string, which, happily, is what part 2 wants. So, of course, we changed part 1 to use dance. It just calls flip dance on this, because it wants to pass things in the other order. But for part 2, we can say, oh, I have this dance function, dance ops, that I want to call a billion times. Please find me a shortcut. And we get the answer back. Kind of nice, right? And so that runs as expected. I'm not sure how much time we have spent on this current puzzle, but it feels like it's been pretty quick. And so I'm going to try to do day 17 today as well. Day 17, spin lock. Suddenly, whirling in the distance, you notice what looks like a massive, pixelated hurricane, a deadly spin lock. This spin lock isn't just consuming computing power, but memory too. Vast digital mountains are being ripped from the ground and consumed by the vortex. If you don't move quickly, fixing that printer will be the least of your problems. The spin-lock's algorithm is simple but efficient, quickly consuming everything in its path. It starts with a circular buffer containing only the value 0, which it marks as the current position. It then steps forward through the circular buffer some number of steps, your puzzle input, before inserting the first new value, 1, after the value it stopped on. The inserted value becomes the current position. Then it steps forward from there the same number of steps, and wherever it stops, it inserts after it the new value 2, and uses that as a new position. It does this forever and ever, well, not forever, a total of 2017 times, inserting 2017 as its final position operation, and ending with a total of 2018 values, including the initial 0, in the circular buffer. Let's think of an example here. Suppose that it were always walking 3 times per insert. It would start with 0, put a 1 after that, walk forward 3 times, ending up like with pointing at this. It would put a 2 after this, and now point at the 2. Walk forward 3 times, 1, 2, 3. Now it's pointing at the 2, so it puts a 3 after that, and then points at the new 3, and so on. And so what they ask us is, what is the value after 2017 in your completed circular buffer? And I don't have day 16 all set up yet because we're doing this all in the same episode, day 17. Day 17, get. Okay. Oops, we need to go back and look at day 17 now. So, since we're working in a list that we want to add values in the middle of, and we want to do this quite often, and do like random lookups, again, it's time for a zipper. Hooray! I went and grabbed my zipper implementation from a previous problem, but removed the stuff I didn't need, and basically we just have these functions. Write and focus are the only things we care about. Recall that a zipper is sort of a list with a pointer, a cursor in the list that you can conveniently move either left or right, and you can query what's at the cursor, implemented by having, as you can see, a value and 2 lists of values. This list is a list of all the stuff to the right of you, and this is a reversed list of all the stuff to the left of you. That way it's cheap to add something to the beginning of this list, which is the rightmost thing on the left list. Fine. And so right is very simple. We looked at this in a previous one, but we basically just pull apart. First, we see if there is no right value, then we reposition the zipper at the far left because we want to have this zipper wrap around. So this is not a correct / normal implementation for a zipper. This is cheating and getting it right for the problem because we want a circular zipper. I wonder if there's a good circular zipper implementation. I don't know. Anyway, and in the normal case, of course, there will be an element to the right, and so we simply pull it off and add it to the front of our things on the left of me. Or rather, add our current value to the things on the left of me, and the value we pulled off from the right would make our current node. And the focus is just x, although, yeah, I do end up calling it. Okay. The other thing that we need is an insert right function that takes a value and adds it to the right end, just to the right of a zipper's position. That's pretty simple. We take the new value and a zipper, and we cons the old focus onto the front of our left list, making it the rightmost left element. We make the new value be our new focus, and we leave the stuff to the right of us alone. We have a function for building a zipper from a list, which we only ever call on the singleton list empties of 0, but oh well. From list is sort of a traditional way in Haskell to build a list-like thing. Or to build a collection of things out of a list. And so what we do is pretty simple, I think. We look at the focus, i.e. what is our current node, after looking to the right of our zipper, after folding step over a zipper starting at being a singleton zipper containing 0, folding that over the list 1 to 2017, which leaves us the question, what is step all about? Step is the function we're folding, of course. It takes 2 arguments. The current zipper and the new value that we wish to insert. What does it do? Well, it iterates moving right, producing, of course, a list of right moves, gets the step size value from that list, and composes that with insert right. Insert right of new, and finally applies all of that to cur the initial zipper. And like, that's sort of it. It's not perfectly efficient, mostly because of this. This reverse is something we do sort of often, and it's a little bit expensive. But that's life. We only... It definitely is not best, but it's fine. It works for this simple, only 2,000 elements. Not something you would want to do a million times, but for 2,000 it's fine. And so that works. Which brings us to part 2. The spin lock does not short circuit. Instead, it gets more angry. At least you assume that's what happened. It's spinning significantly faster than it was a moment ago. You have good news and bad news. The good news is that you have improved calculations for how to stop the spin lock. They indicate that you actually need to identify the value after 0 in the current state of the circular buffer. The bad news is that while you were determining this, the spin lock has just finished inserting its 50 millionth value. What is the value after 0 the moment 50 million is inserted? So, I didn't try just running this 50 million times instead of 2,000 times. Maybe it would have worked. It would be interesting to find out, wouldn't it? Let's say we did that. Well, this won't tell us the answer at all. We could afford, I suppose, to to be 1,000 times faster than this. It would take 10 minutes, but we could wait that long. The problem is that we wouldn't be 1,000 times slower, right? We would be way, way slower because we're doing sort of work that is at least linear with the time of the input and possibly quadratic. And it would balloon out of control, the amount of time that we take. So that doesn't seem like a winner. So what could we do instead? I spent quite a while thinking about this because no obvious alternate algorithm suggests itself. I was trying to think of how could I simulate this, how could I shortcut doing this simulation, right? Maybe, you know, we're stepping forward 300 steps, I think is roughly what our input is. And, you know, most of the time our input has many more than 300 values in it. And so this whole process of zipping forward this many times, maybe we could improve it by like interleaving our list with a list of the new values we know we're going to put in before we wrap around, and then finally doing that wraparound only when we need to. It's not even clear that that would be faster if we were smart enough to do it. But finally, I came up with something which was, we don't really care about the whole list at all anymore, right? We only care about what's after 0. And it's not so hard to calculate what's going on at position 0, because you can model what your current position is in the list and what value you're inserting there without having to track the whole list. You just have to know its size, right? And so that's what I ended up doing. I said, forget this whole zipper nonsense for part 2. Instead, part 2 is a function that completely ignores all the stuff we did for part 1. Except, of course, for parsing, which was, you know, pretty simple. And it basically says, here's, you know, part 1 is too slow to do 50 million times. But here's an operation we can do 50 million times, just like a little bit of number crunching. We scan over a tuple. What we're keeping track of is a tuple, specifically the position that we are inserting after and a value that we will insert there. The value that was there, I guess. Yes. And here, at each step, we choose a new value that we will put there. And conveniently, the new value is the same as the size of the list. And so we don't need to track the size separately or anything. We can just use this one number. And from the old position, notice we're ignoring the value here, by the way. This doesn't get used. From the old position and the new value we want to add, we can compute a new value and what we added there, which is just add together the old position and the step size, take that modulo the current size, and put an n there, and you're done, right? So in that way, we can produce a list of all the positions and what was inserted there. Now, that's only what the position was when we inserted the thing, but fortunately, 0 is always the same. Nothing ever gets inserted before 0, only after 0, and so we only care about inserts that happen at exactly position 0. Therefore, after we've run this scan, we can just filter for times when the position was equal to 0, and get the last such value and say what was its value at that time. And we have the answer. Or so it seems. When I run this program, it gives me the wrong answer and points out, very interesting. You computed the right answer for someone else's input. You know, are you logged into the wrong account? Are you cheating? Well, maybe you're just unlucky. I was unlucky. So now let's look at the last change. Last change that I did here, which was I had an off by one error somewhere. And in the process of fixing the off by one error, I ended up extracting all of part 2 into a separate function called after 0 that takes as an argument the number of inserts. This was to help me run it on the test input. I mean, does this really need to be its own separate function? Maybe, maybe not. But I extracted it out while debugging, and then I left it there because it seems fine. And you can hopefully see that the only change is this. Because, remember, this is the position we are inserting after. And so in order to wrap around, we need to add 1 to get our current position, then add the step size, then compute mod n, and now it'll point at what we're about to insert after next time. So maybe there's a cleaner way to have done this if we had worked with 1 instead of 0. I don't know. But anyway, there's this off by 1 error. What a bummer. And after doing all of that, the program computes the correct answer. So this was one where the work done ahead of time of like modeling the problem domain, well, on the one hand, it didn't really pay off because part 2 needed a completely different model of the domain. But on the other, we didn't really model the domain at all, right? We said, oh, just have a zipper and like put some crap in it and see what happens. Because that was really what the domain was just like operate on a list of things. Good luck. I don't know. So on the other hand, it did feel rewarding to think about the problem in a different way enough that I could figure out how to short circuit like doing all of the hard work and get this down to a manageable size. Anyway, so that's it for day 17. Day 18 may be a while. You may notice here that I've only done part 1 of day 18. Day 1, part 1 took some time, but part 2 is like, in principle, it seems like it shouldn't be hard, but my solution for it really sucks. And I don't know how to debug in Haskell properly. Like, there's a bug somewhere. It's not a type error as far as I can tell. I can't figure out how to make it a type error. And so I don't know how to ask the compiler for help. I don't know. Maybe I'll record other ones before I finish 18. But anyway, of course, if you're watching this from the archives, so to speak, then you don't have to worry about me being stuck on day 18. And by the way, you can see that day 18 is one of the hardest ones of the year. There's way more people who have done part 1 but not part 2 than for any later problem. There's a couple earlier problems, like day 7 recursion. Apparently, a lot of people haven't worked with recursion, which, sure, understandable, makes sense. But anyway, like, I think day 18 is the last big hurdle, at least for part 2. The part 1s, some of them they don't look super, super hard. A couple of them look a little bit tricky. But anyway, spoilers, I guess, because we're not doing any of those problems right now. Thanks for watching, and I'll see you next time.